Okay, this is 1.1, number 14 in your book, and the directions say to substitute y equals e to the rx, right? So this function given, it's an exponential function, into the given differential equation, which we have here. This is a second order differential equation because the highest derivative is 2. And so we say the order is 2. Let's see, to determine all values of the constant r, right? This constant r for which this function is a solution to the differential equation. So here we're just going to substitute this function into y. And so we have 4y double prime equals, well, actually let's substitute. Let me erase that. So 4y, and my y is e to the rx, and I'm going to take the second derivative equals y, so e to the rx. So again, all I did was substitute the value here. And we can even rewrite this as 4 times, so we're really going to take, we're going to have e to the rx, so we're going to take the derivative first, and then after our simplification, then we're going to take the derivative again, right? Because we have the second derivative. So here are my two derivatives. And the right-hand side, there are no derivatives, so I can leave that alone. So let's differentiate. So we have 4. Well, what's the derivative, right, of e to the rx? Well, remember that's e to the rx times the derivative, right? This is using the chain rule, the derivative of the inside function, or that was just our kx in the common derivatives in one of the videos I did. So this is just times r, but remember this is just the first derivative, so let me keep my brackets here, erase that, and equals e to the rx. And again, let's take the derivative again. So 4, and right, r is just a constant, so we're just going to carry this along. So e to the rx, so e to the rx times r, right, the derivative, and then this r is, right, just drops down. So equals e to the rx. And we're pretty much done differentiating. Now let's just simplify a little. So we have 4e to the rx, r squared equals e to the rx. And I'm going to go ahead and bring over my e to the rx to the left-hand side. So I'm going to say 4e to the rx, r squared minus e to the rx equals 0, and the reason I did that is because I have a common factor of e to the rx in both terms, so I can factor this out, right? So that's my greatest common factor. So e to the rx, and my factor left over is 4r squared minus 1 equals 0. And we can use a zero factor property here, so we know that e to the rx is equal to 0, or 4 squared minus 1 is equal to 0. So we've differentiated, we substituted our value, right, our function into our differential equation. But again, here we're not verifying, right, because we don't know what r is, and so we're determining r. And so here, the question is, when is this function equal to 0? Well, this is an exponential function, right? It's an exponential growth or decay depending on what r is. If r is positive, it's exponential growth. If r is negative, it's exponential decay. So, I mean, here's just a quick sketch of this is e to the rx when r is positive, and here's our exponential decay when r is negative. So when does the graph hit 0? When does it intersect 0? Well, it never intersects 0, right? There's actually a horizontal asymptote at, let's actually draw that in. Right? There's actually a horizontal asymptote, right? It's not defined at 0. So this is not possible, right? This is not possible. But what about the other factor? And this one's pretty easy. I mean, there's a couple different ways you can do this. We can, I'm going to go ahead and add 1 right to both sides. R squared equals a fourth. And then we can use our square root property. And we get R is 1/2 or -1/2. If you wanted to use the difference of two squares, you're going to get the same solution. It really depends on how you want to factor this polynomial. Right, so preferences here. So you can say this is 2r minus 1 times 2r plus 1, right? They're conjugates. When you solve for, when you set these two guys equal to 0, you're going to get a half and -1/2. So R, we determined what R was. R was a half and -1/2. Again, there's no R here. It doesn't exist. Again, algebraically, if you wanted to solve this equation, right, you'd probably, let's use a different color here. Let's do purple. You would normally ln both sides because ln and e, right, give you 1. They're inverse functions, and, right, from logarithms, Rx equals ln of 0. But this is bad because your function ln, that graph, right, it's not defined at 0. Right, our ln graph looks something like this, and again, there's a vertical asymptote there, so it never actually, this graph never intersects the y-axis, so, I mean, it has to be greater than 0. So again, that's an algebraic way of looking at it, or if you want a graphical approach, that's fine. So that is number 14.